Our journey of studying Cauchy problem for general nonlinear equations has started in the last lecture, that is lecture 2.10. Today we continue. The outline for this lecture is, first we recall once again the hypothesis and notations involved in general nonlinear equations, and in the last lecture we started our search for a characteristic direction. We were not yet successful. Today the search resumes and we will find a characteristic direction for the general nonlinear equation, and then resulting characteristic ODEs are incomplete, we are going to see that, and therefore we need to extend the system of characteristic ODEs to a new system, which is system of equations for characteristic strips. So, let us recall the notations and various hypotheses which are involved in the Cauchy problem for general nonlinear equations. F is the function which is going to define as the general nonlinear equation. The arguments of f have been written as x, y, z, p, q, so defined on for 5 tuples. So, lying in omega phi, which is an open subset of R phi. Such an f defines the most general form of a first order nonlinear general nonlinear PDE by f of x y u u x u y equal to 0. Though we know that this class GE contains in it linear equations, semilinear equations and quasi-linear equations, but we refer to this kind of form of general equation as fully nonlinear equation or general nonlinear equation. So, hypothesis on the function f which defines the PDE are that f must be a C1 function on its domain of definition, which is equivalent to saying that the function along with all first order partial derivatives of all the arguments which are x, y, z, p, q are continuous functions on omega phi. And we need to assume that fp and fq do not vanish simultaneously at any point in omega phi. Omega 2 and omega 3 denotes the projections of omega phi to xy plane and xyz space respectively. The Cauchy data is prescribed by gamma x equal to fs, y equal to gs, z equal to hs for s belong to an interval I, and these functions are C1 functions on the interval I, and we assume the projection of gamma to xy plane, which is denoted by gamma 2, is that gamma 2 is a regular curve, which means f primes and g prime do not vanish simultaneously at any point on the curve gamma 2. Recall that Cauchy problem means we need to find a solution of the equation which satisfies this u of fs gs equal to hs. In other words, fs gs hs belong to the surface z equal to uxy. Now, let us recap from the last lecture the search for a characteristic direction. So, we wanted to extend the ideas from quasi-linear equations to general equations. The idea in quasi-linear equations was construct integral surface using characteristic curves. To think of characteristic curves, we need to have a characteristic direction. So, how do you obtain a characteristic direction for GE? That is the question. Recall, for quasi-linear equations, the equation gave us a characteristic direction. The equation QL is AUX plus BUY equal to C. What we observed is, if you take any point on an integral surface given by z equal to uxy, the normal direction at P is ux uy minus 1, and the equation tells that ABC is a direction in the tangent plane at P. This observation led us to define the notions of characteristic system of ODE and characteristic curves. Once again, there is no automatic choice of such a characteristic direction for general equations. So, then we went on to consider this family of possible tangent planes to possible integral surfaces through a point for general nonlinear equation. Take a point P naught in omega 3 we get a one parameter family of possible tangent planes given by T1 and T2. What is T1? T1 is simply equation of a plane passing through x 0 y 0 z 0, but by restricting Fp to satisfy T2 will mean that this is going to be a tangent plane to a possible possible integral surface. It should satisfy these conditions T1, T2. Note this uses only the information coming from the equation. Okay, we are not pretending that we know the integral surface, that is not needed. Now we observed that the T2 for quasi-linear equation is this, and as one of them is non-zero, we know that A or B has to be non-zero by assumption in the quasi-linear equations. We assume B is non-zero, then we can solve Q as a function of P. In fact, it is a linear function of P, that is what makes things much simpler, and T1 for QL becomes this after substituting for this. So, this is a family of possible tangent planes. We have explicitly got one equation. So, this represents the Tp represents one parameter family of possible tangent planes indexed by a parameter. For general equations, we have to have both the equations. Okay, if you are able to eliminate P or Q from here, that is express Q as a function of P, go back and substitute here, then once again you have only one equation like this. Okay. In the case of quasi-linear, it was very easy to express Q in terms of P, but in case of general nonlinear equations, it is not clear. So, this is still a one parameter family of possible tangent planes at the point P 0. Now, envelope of one parameter family of tangent planes for QL we computed, it turned out to be this. What is this? This is nothing but the characteristic direction at P0. This is a line passing through the point x0, y0, z0, and the direction ABC is a characteristic direction. So, therefore, the plan for getting a characteristic direction for GE is like this: obtain an envelope of one parameter family of possible tangent planes for GE, which is this. So, get the envelope of this and choose a direction in the tangent plane for the envelope. This plan will be successful because we have a lemma that we proved in the last lecture, which is here. If you take a one parameter family of surfaces given by z equal to gxy lambda, and you find its envelope, which is this z equal to gxy, and c lambda denotes the intersection of the envelope and the family, then look at the second conclusion. The envelope and s lambda touch each other. That means, wherever they intersect, which is along c lambda, the intersection is precisely c lambda, at every point on c lambda they share the tangent plane. Therefore, if you can find a direction in the tangent plane for the envelope, we are done. That will also be a tangential direction for s lambda. That will also be s lambda. So, let us resume our search of characteristic direction. So, this is T1 and T2 that represent one parameter family of possible tangent planes at the point P 0. Let us find the envelope, that is what we need to do. To do that, we need to assume that Q can be expressed as a function of P in a differentiable way, so that this equation is satisfied. In other words, we are solving f of x 0 y 0 z 0, P q equal to 0, and Q is expressed in terms of P. Question is it possible? It is always possible to find such a function locally. Implicit function theorem tells you come with a particular solution and a non-zero or invertible derivative, I guarantee the existence of such a function. This is typically what implicit function theorem says. Now, we will go to the implicit function theorem with a particular solution, that means you first find out a P0 Q0 real numbers such that f of x 0 y 0 z 0 p 0 q 0 is 0. That means we have the particular solution. Now, we need to see what is this non-zero derivative, and f q at this point x 0 y 0 z 0 p 0 q 0 is non-zero. Please note, when we are applying implicit function theorem, x naught, y naught, z naught is fixed. So, it is only as a function of p and q that we are trying to solve, this is equation 1. Okay. So, f q is non-zero. If you assume, then implicit function theorem guarantees existence of such a function, but locally. That means, in an interval containing p 0, you can express q as a function of p. That is the implicit function theorem. Therefore, the one parameter family of planes becomes simply one equation now, because I have solved q in terms of p and I put it here. Now, only thing to do is differentiate this equation with respect to p and we get this equation. These two equations. You differentiate this equation, you get 2a, differentiate TP equation, you get 2b. From 2a and 2b, you can eliminate q prime p and we get this, x minus x naught, y minus y naught is proportional to fp fq. Okay, something we got. Now, what is this p naught p q p? P naught actually x naught, y naught, z naught. F is a function of 5 variables, right. We need a 5 tuple here. For want of space here, I have just made it a small notation p 0. It stands for this. Using this and the equation for tangent planes, which is Tp here, we get the curve of intersection, and that is this. Okay, x minus x naught is proportional to fp, y minus y naught is proportional to fq, therefore, z minus z naught is proportional to p fp plus q fq. That is what we have written here. So, this is a line, right. Cp is a family of lines, of course, indexed by p. The same thing was actually one single line, it never depended on p for a quasi-linear equation. All of them pass to the point x naught, y naught, z naught and having a direction fp, fq, p of p plus q of q. The 3 tuple which is given in 5 is non-zero, because we have assumed that fp square plus fq square is not equal to 0 throughout the domain of f. That is a hypothesis on f. An envelope of the family of planes Tp by definition is a union of Cp, that means union of these lines. So, envelope is a cone having vertex at p 0. So, visualize the way a family of lines passing through a point p naught looks like. For example, you have this point p naught, right. So, imagine lines in 3D, okay, like that. So, that is how looks like a cone. This is called Monge cone. Thus, we have a Monge cone field defined in omega 3. So, omega 3 is in R3 some set, okay. At any point you have a cone sitting there, at another point you have another cone. Like that. So, every point you can attach a cone. So, this is called cone field, similar in spirit to a vector field. To any point, if you attach one vector, associate one vector, it is called vector field. If you associate cone, it is called cone field. That is, to every point of omega 3, a Monge cone is associated. For quasi-linear equations, the Monge cone degenerates into a straight line, because we observe that the envelope is actually a straight line, it is independent of p. So, therefore, it is just one single straight line. So, the Monge cone field reduces to a characteristic vector field in the case of quasi-linear equations. Now, each of the lines Cp corresponding to each fixed p is a generator of the cone. Generator of the cone means it is a line in the cone. So, you have a, for example, you have a cone like that, you have a line here. So, at a point on the cone, if you take tangent plane, okay, that line is going to be there on the tangent plane. Therefore, what we wanted was to look at the envelope and take one direction in the tangent plane of the envelope. Now, here it is very nice, tangent plane of this cone at these points, the one of the direction is clearly the line Cp. So, we can take that Cp to be characteristic direction. So, a characteristic direction for GE is found for every p in omega 3 and every pq. We no longer require q of p here, pq. After all, if q is a function of p, q is some value, right. It satisfies this equation still. We have found a characteristic direction at p. What is that? Fp, Fq, Pfp plus Qfq. Now, we have to look at the characteristic ODEs. We are going to say they are incomplete, we will see why. So, inspired by the success in finding an integral surface using characteristic curves, we hope to repeat the same for GE also. In QL we were successful, so we hope same thing happens for GE as well. So, we are in search of curves in omega 3 which have tangential direction equal to the characteristic direction that we just found, which is this Fp, Fq, Pfp plus Qfq at each of its points p. Such curves we are looking for. Now, Pq of course depend on the point xyz, right, they satisfy this equation. So, it depends on xyz. Let us write a curve having a characteristic direction. So, let j be an interval, 0 belongs to j, gamma p0 be a curve given by xt yt zt as t varies in j, such that it passes through the point p0 at t equal to 0 and it has a tangential direction which is characteristic direction at each of its points. This is what we would like to call a characteristic curve. Therefore, the following system of characteristic ODEs hold along gamma p0. So, dx by dt, dy by dt, dz by dt are Fp, Fq and Pfp plus Qfq, and at t equal to 0 we want to be at the point x0, y0, z0. So, fine. Now, why is it incomplete? I do not know what is P and Q, that is a problem. Okay. Let us denote the above system by chara ODE exactly like we used for quasi-linear equations. The solutions of this, its images will be characteristic curves. Only thing is that this is not it does not determine characteristic curves, that is a problem because there are PQs here. It is not solvable as the unknowns PQ appearing in it depend on xt yt zt via this equation f of xt yt zt PQ equals 0. P and Q are also depending on t. Thus, we also need to determine P and Q as functions of t. Since xt yt zt themselves are unknowns, there is no hope of solving for P and Q from this equation. And note, this is not the case for quasi-linear equations because characteristic ODE never involved P and Q. And this is the second difficulty in extending the ideas from the quasi-linear case. What is the first one? Finding a characteristic direction. That was the first difficulty we have overcome, and second difficulty we will overcome by supplementing two more equations, for one for P and one for Q. So, how to find the equations for PT and QT? We need to supplement chara ODE system with equations for PQ along the curve xt yt zt, and what should be the property? PT QT minus 1 should be the normal direction to a possible integral surface, they are not arbitrary functions. So, we have to determine 5 quantities xt yt zt and PT QT, and not just the 3 quantities because we are unable to determine the 3. We would have been very happy if you had got xt yt zt, we could have proceeded, but the equation for xt yt zt involved P and Q, therefore, we need to find P and Q also. So, geometrically speaking, what we are saying is we have to determine not only a curve, but also a tangent plane to a possible integral surface that contains this curve. So, in other words, we are trying to find a curve like that. So, suppose this is the point xt yt zt. So, we want to find something like that PT QT, of course minus 1 I write, but then it is okay, minus 1 there is nothing to find. So, we need to find this. So, let J be an interval in R and gamma be a curve given by x equal to x t, y equal to y t, z equal to z t, be a curve having tangential direction as char dir, that is characteristic direction at each of its points, where p t q t satisfy this equation f of x t y t z t p t q t equal to 0. The phi tuple x t y t z t p t q t is called a characteristic strip. Okay, maybe you may put like that because we are saying tuple, but it is okay, even without that it is fine. All these 5 together is called a phi tuple, that is called a characteristic strip, and the point x t y t z t is called support of the characteristic strip, because that is the point at which you are putting a plane with the normal p t q t minus 1. So, let us illustrate that pictorially. So, here there are 2 points I have considered, indexed by t equal to t 0 here and t equal to t 1. So, x t naught, y t naught, z t naught is a point, this is a tangent, this is a plane with the normal p q minus 1, this is another point where the normal is p q minus 1. So, it can be strip can be thought of as a point along with an infinitesimal plane element passing through that point x t y t z t with the normal direction p t q t minus 1. Now, how do you get equations for p t q t? So, here we assume some more nice properties about the solution u. See, u is supposed to be a solution to first order PDE, we have not yet found, but we are assuming that it is C2. Is it okay? That is a question. It is okay, because we are going to use this only to derive certain equations, and for deriving equation you assume what you want, does not matter, but after getting the equations then you should show that solution exists. There you should not suppose that C2 etc. Okay. We will comment on this in the next lecture also. So, this is only to derive the equations for PTQT that we are assuming U is C2. So, how do we derive the equation for PT? What are at our hands? This equation f of x y u u x u y equal to 0, differentiate that with respect to x. So, first is f x, here I am using the zeta to stand for the x y z p q. Okay. So, f x, and then with respect to z, in z you have u x y, therefore, you need to differentiate f z and u with respect to x, then with here also p f p, and then whichever is here with respect to x, which is u x x, and here it is f q and u x y or u y x equal to 0 at every point in omega 5 where we use this notation zeta equal to x y z p q. Yeah. No, actually this is zeta is not x y z p q, it should be x y, we have to substitute x y z p q equal to x y u x y u x x y u y x y, that is what it is, because we are going to differentiate here, this u is a function of x y, u x is a function of x y, u y is also a function of x y. So, that is why we get this by chain rule. Yeah. And x t y t z t is a point lying on the integral surface z equal to u x y. We require the following thing to hold, namely p of t I want it to be like u x. So, p of t is equal to u x of x t y t, we are demanding this, okay, because p t q t minus 1 should be such that f of x t y t z t p t q t should be equal to 0, right. So, p is supposed to play the role of u x along the curve x t y t. So, that is my p t, we want this. So, on differentiating the above equation with respect to t and using chain rule, we get p prime t is equal to, t appears in both the variables. So, differentiate this with respect to x u x x at the point x t y t into derivative of x with respect to t, that is x prime t, and differentiate this with respect to y, that is u y x at the point x t y t into derivative of y t, which is y prime t. Since characteristic ODE hold for x t y t z t, denoting zeta t equal to this phi tuple x t y t z t p t q t, we get p prime t is equal to u x x, x prime is f p, y prime is f q. So, we have got this equation for p prime. And from the equation 7, that is the one we got after differentiating f of x y, yeah, this one, this equation. And here we almost got an equation for p prime. The only problem is there is u x x and u y x, we do not want that, right. Equation of p should involve only f, it can involve x t y t z t, no problem, but not u x x and u y x. So, that needs to be removed now. So, we solve for that which we do not want in terms of what we know, f x p is what we want to find, f z which we know. Therefore, p prime t equal to this and now becomes p prime t equal to minus f x plus p f z. This is the equation for p prime. Similarly, we do for q. What do? We look at the same equation g e, differentiate that with respect to y, we get something. Then we propose the value for q t. Q t is supposed to be u y of x t y t, differentiate this with respect to t. It will involve this u x y and u y y, eliminate this using the previous equation, I think it is equation 11, and then you get an equation for q prime. X is replaced by y, that is the only change, p is replaced by q. So, this is the equation for q prime. So, we got the equation for q prime also. So, this is the system where the first 3 we have obtained or we have proposed using characteristic direction. We realize that p q also depend on x t y t z t, and we said we have to find equation for p t q t, and we have appended Cara ODE with these 2 equations. Now, it is called Cara strip ODE, equations for the characteristic strip. Now, there should be no problem because x y z p q, here also x y z p q, anything else f, we know f, therefore, we know f p f q. So, no problem. Of course, this is a nonlinear system of ordinary differential equations. How to solve this? We have to solve this to get the characteristic strip, and that we will do in the next class. So, let us summarize what happened so far. We saw that the quasi-linear equations has a characteristic direction right away given by the equation QL. GE gives only possible tangent planes, and using the idea of envelopes we found characteristic directions for GE, and we observed that the system Cara ODE is incomplete. So, the system is supplemented with 2 more equations, and we got characteristic strip equations, ordinary differential equations for characteristic strip. So, in the next lecture we are going to take up the Cara strip ODE system, which is a system of 5 equations, nonlinear equations, and we need to solve them. And what is the strategy in quasi-linear equations? We take the datum curve, take a point on the datum curve and pass a characteristic curve through that. So, now if you take datum curve, what is known is only x, y, z values on the datum curve, namely fs, gs, hs, which are given to us. We will use them as initial conditions in the characteristic system of ODE in the quasi-linear case. But in the general nonlinear equations case, we have 2 more equations, which is pt and qt, equations for them. Therefore, we should know on the datum curve what should be the values of this pt qt on the datum curve. So, that is what is called initial strip. So, initial data or datum curve is given, that must be extended to a strip, and that is called initial strip. Using initial strip and using the initial conditions coming from the initial strip, we will solve characteristic strip ODEs and get characteristic strip, we will determine characteristic strip, and from there will come characteristic curves, and from there we try to take their union and get the integral surface. So, these steps will be implemented in the forthcoming lectures. Thank you.